Hi, everyone. Welcome to lesson 14. So this lesson is about force representations. So we're going to learn here how to identify the forces that act on an object and also to represent those forces with something we call free body diagrams. So what is a force? Well, sometimes the easiest way to explain what a force is just to simply say that it's a push or a pull. That might be a very simple definition of what a force actually is. And a force, what's important about it is it always has to act on an object. It has to have something to act on. So for instance, here we have somebody pushing on a door or pulling on a door. Right? And a force also requires something we call an agent, okay? Something that is doing the acting, something that's doing the pushing, the pulling. So in this case, if you kick a ball, well, then your foot is the agent. It's the cause of the force that's exerted on the ball. So the foot here would be the agent. And the ball would be the object that the force is acting upon. Force is a vector quantity, which we're very familiar with. And so we know that a vector is something that has both magnitude and direction. And so we can see here, we have a magnitude of 70 pounds. And we can see that there's a direction. We can see it's being pushed to the left, but not quite to the left. But with respect to the negative x-axis, it's moving with a direction of 15 degrees north of west. Okay. All right, and we see here also it says F1 equals 70 pounds. So we symbolize force with the letter F, capital F. And if you want to be extra special about representing it as a vector, you could put an arrow on the top of it. So there are a couple different categories of forces. So the main one we're going to consider, the main ones we're going to consider are called contact forces and field or long range forces. So with contact forces, there has to be two things have to touch. So for instance, your foot, if you kick a ball, your foot has to touch the ball in order for you to apply a force to it. Whereas with a long range force, or sometimes we call a field force, two things don't have to come into contact. So we're very familiar with the example of gravity. And gravity, it's actually the force due to gravity is a long range force. And so when a cat falls or when you drop your keys, the earth doesn't actually have to touch the cat or the keys in order for it to exert a force on it. So these are long range forces. Okay, so how do we represent forces? Well, we said the symbol for it is the capital F. But we can also, since it's a vector, we can represent it with an arrow. So for instance, here we have a person pulling on a box. All right, so with a rope. And so the rope is the agent, since the person is not actually touching the box. She's pulling the box with the rope. And so since it's a vector, we can represent force with an arrow. And so since she's pulling it to the right, well, we have a force arrow to the right. And we can also remember from our study of how we represent vectors pictorially, the length of the arrow has to do with the magnitude of the force. So if she pulls with more force, then there'll be a longer arrow. If she pulls with a very little bit of force, it'll be a shorter arrow. And the arrow points in the direction of the force. Okay. And we could also see here how this image applies the particle model to the box. So rather than drawing the whole box, we can just symbolize its position with a dot. And sometimes that makes our life easier, which we've seen in previous lessons where we've applied the particle model. Okay, and one term we're going to use very frequently is called net force. So the net is sort of like all the forces. So you've heard of things like your net income versus your gross income. Okay, so net force is all the forces that we're talking about that are happening, that are being applied to an object. So this is important if we have more than one force applied to an object. Okay, and so if we have, say, we're pulling on a box here, and say one person pulls to the right on this black rope, and another person pulls down on this black rope, well, there's now two forces going on, and so you could probably predict that the box will move in some sort of direction like that. Okay, maybe if the person up here is pulling with a larger force, then it might move more in this direction. Okay, if the person on the bottom just stops pulling, well, then it'll all move in that direction. And so we can represent the net force as that capital F for force, and then a subscript net. Right, and since it's all the forces, sometimes we call it the sum of all the forces, and so we can use the mathematical symbol for sum, that capital sigma, and it's a sum of all the forces. So if I put Fn, then it's the n amount of forces, or if there's 3 forces, then n is 3. Okay, so here we have, let's call this force 1 pulling to the right, and force 2 pulling down, call them F1 and F2. Then my net force is just F1 plus F2. Okay, and it's important because it's a vector sum. Forces are vectors, so we have to do a vector sum. Okay, so if we were to add these pictorially or graphically, remember that we have to add vectors head to tail. So if I were to take vector F1, maybe this is F1, and I'm going to add F2 to it. We do it head to tail, right? And then we'll have a resultant vector. Maybe we could just call it F, going in that direction. Okay, and then we could, if we want to be very, very precise and put this on a grid, a graph paper, then we could draw the length of the arrow to correspond with the magnitude of the force, and we could put the direction, and we use a protractor and get the exact direction if we wanted to. All right, so let's say, that the top force, let's call it 3, and let's call, so I'll call this F1 equals 3, F2 equals 4. Right, so how could we symbolize that mathematically? Well, this could be 3i hat plus 4j hat. Okay, or we can look at this we can draw the diagram like this, where we have essentially where it's drawn head to tail, and we formed a nice right triangle. Well, then we can use the Pythagorean theorem right? A squared plus B squared equals C squared. So F1 squared plus F2 squared equals F squared, right? That will give us the magnitude. And then we can use, if we want to find direction that it's going to move in, well, then we can use one of our trig functions to determine that. All right, so we'll do some practice with that. And right. And okay, so one way, if we're going to draw a situation, we call it, when we're showing all the forces acting on an object, like sort of how we did here, we call that a free body diagram. So that's what we mentioned in the second objective for today. So a simple free body diagram could just be like what we drew here. Okay, or if we want, we can represent it. You can use the particle model and just represent it, that box with a dot, and we say, okay, we have F1 and F2. And that's probably the simplest free body diagram that you could draw. Okay, just a way to represent visually all the forces that are acting on an object. And so it may seem like, what do I need that for? But I'm telling you, it really, really helps you to visualize a situation, a scenario. So we want you to get in the habit of drawing these free body diagrams. It's important. Okay, so the gravitational force, so the force due to gravity, this is the pull that the Earth has on an object that's near its surface. Okay, so what causes things to fall? So if we were to, let's say, I'll make Earth here, nice green Earth, and maybe if I wanted to do a free body diagram of the cat falling, I wouldn't really have to put Earth there, but we know that things fall toward it. I could just represent the cat with a dot. And if it's falling and that's the only force acting on it, well, I could just put it straight downward. Right? So the gravity, the force due to gravity, always points vertically straight downward. And we could symbolize it as F with a subscript G for gravity. And so the agent that's actually applying the force, since we have a long range field force here, it's the entire Earth itself that's applying the force. Okay, so force due to gravity is one important force. Another important force is that we're going to work with, especially a lot, is tension. And so when a string, when you have any kind of thing that's you pull with, right? Or a string, maybe a rope, a wire, a cord, when it pulls on an object, it exerts a contact force, and we call this force tension. So maybe this is your iOLAB device, and you have a little eye hook on it there, and you can attach a string to it. Maybe you can just kind of pull it if you want. And when you do that, you apply some tension to that string. Okay, so the direction of the tension force is always in the direction of the string that where it's being pulled with. Okay, we symbolize tension just simple with a capital T. Another important force is called the normal force, and if we think about, before we go to that, I can just draw the tension on here. If I were pulling it to the right, I could just draw it like that. Okay, so normal force, if an object is just resting on a surface, we know that gravity is technically, even though it's not falling, gravity is still applying a force to it. It's trying to pull it down, but the surface it's sitting on is preventing it from doing so, which keeps the object at rest. Okay, and so we say that there's another force that kind of counteracts gravity, the pushing up of the surface. It acts in the opposite direction as gravity, and since it points the opposite direction, perpendicular to the surface, then we call it the normal force. And we can symbolize that with F subscript n, or sometimes you'll see it in your book or homework system might just be a capital N or lowercase n. So it's just kind of, those are the frequent ways to represent the normal force. Okay, and so the normal force is important because if you look at bathroom scales, what a bathroom scale actually does is you stand on it. All right, in my pathetic example for a person standing on a very large scale. And we know when you stand on it, gravity acts downward, but the reading on the scale actually comes from, inside the scale, there's usually some sort of springs that are applying a force upward, and that upward force is the normal force, and that's how you tell your weight. And we'll get a little bit more into detail with springs and normal forces in future lessons. Then another important force is friction. Friction is a contact force. Two things need to touch in order for friction to happen. And so there are two types of friction. There's static friction. Okay, and static friction, and the word static you might be familiar with, usually means that something's at rest. And so static friction is this contact force between an object, a stationary object, and the surface that it's in contact with. So for instance, if your car, like in the picture here, runs out of gas, and it's a flat surface, it's not going to really move anywhere, right? And so this person here could be pushing on it with all the force they want, and it doesn't move because there's some we call static friction between the tires and the ground. Okay, so the static friction always opposes any attempted motion, and so this person is applying a force to the left, but the static friction, since it's opposing that motion, technically it points in the opposite direction. Okay, it's trying to hold it back, it's trying to keep it from moving. Okay, and so it points in that direction, opposite direction as which the object would, if the object did move, then static friction points in that opposite direction. So I'll just put a little note here. It's the force between stationary object and a surface. And it wants to resist motion. All right, so that's one type of friction. The other type of friction is called kinetic friction. And kinetic, you probably know the term kinetic is referring to motion. And so it's the force that exists between a moving object and the surface that it's on. So it's essentially the same definition as static friction, but you swap that word stationary to moving. Okay, so when an object is sliding along a surface, or rolling along maybe, then the surface exerts a contact force that also opposes that motion. Okay, so we call this kinetic or sliding friction. Okay, so just like static friction, it always points in the opposite direction that the object is moving. Okay, so even if this person got the car moving and it started rolling, well, there's still technically some friction between the wheels, the tires, and the ground. And so even though it's maybe moving to the left, kinetic friction would still be pointing in the opposite direction because it's trying to still resist that motion, because there usually is friction in real life, although a lot of times in physics we try to ignore it just to make a situation more simple to understand. So I'll just put a definition here: the force between a moving object and a surface. It too resists motion. And so to symbolize those, we'll call static friction F with a subscript S, and we'll call kinetic friction F with a subscript K. All right, and so if we have the iOLAB device sitting here on the table, and if we say we try to give it a push, okay, maybe we try to push it to the left with a certain force. Maybe I'll just put APP, applied force. Well, we know that gravity will be attempting to pull it down, but it's on a surface, so the normal force will push back in an equal and opposite direction. Okay, and so if we try to push it to the left, and it doesn't move, well, then static friction is going to hold back. Okay, and yeah, so we'll get into a little bit more of this in the next lesson of when does static friction stop and kinetic friction start. But that's just kind of an introduction here to friction itself. So another type that I just want to introduce you to, because I think one of the homework questions talks about drag. And drag is essentially kinetic friction in a fluid. And fluid is anything that flows. It doesn't necessarily have to be a liquid. Things that flow are liquids and gases, like air. So air is a fluid. And so we have this friction. We know that if you go skydiving, you'll fall for a certain distance until the air pushing on you is strong enough that you really are feeling it. And it actually will slow you down, or not slow you down, but it'll prevent you from accelerating more, and you'll reach what you call a terminal velocity. And we use drag. So in the age of the space shuttle, we used to use these crazy parachutes. Must have had a lot of strong ropes in here to withstand the tension caused by that pull, but it would help in the landing. And we also know that with cars, because we're going so fast, we get a lot of wind, that drag. And if you're driving along the Mass Pike or something at 65 miles an hour and you put your hand out the window, there you could feel that force. And so unfortunately, we want to get places fast, but that air actually can deter on things like gas mileage. And so if you go into maybe some sort of mechanical engineering, you might need to learn about drag in order to try to design the best cars so that the airflow will move around it with the least amount of friction, right? Because if you're going one way and the friction is pulling the other way, well, you already got friction from the tires. You need that so that you can stop, or else what's the point of starting? But then also the drag is holding you back. You're spending more gas than you need. So so designing cars to allow the airflow through it better is important. And so we ever look back at some of the old cars from the olden days, you can see my terrible drawing skills, but they used to be very, very boxy kind of things, and it was very that was not too good for gas mileage, but gas was so cheap back then that didn't really matter, and now that it's getting more expensive, it does matter. And so we saw several years back when gas prices jumped over $2.50, $3 a gallon for the first time, people started freaking out, and then all of a sudden we started seeing companies coming out with cars with gas mileage of 30, 40 miles a gallon and more. And so the technology was there, but nobody really cared enough until the prices went up. So, all right, so we'll just look at one question here. If you want to give it a try, I'll pause for a moment. But it says a steel beam hangs from a cable as a crane lifts the beam. So what forces act on the beam? So if you want to take a moment and look at the different options there, I'll just pause for a second. Okay, so I'll just draw a little beam here. This is the beam, and we know that gravity is going to act on it. Okay, and the crane's lifting it with a cable. Okay, so there's some tension in the cable. So what forces act on it? Okay, so the best response here is B, gravity and tension in the cable. So if you thought, well, why not a force of motion? Well, if you looked at all the forces that we learned about in this lesson, there's no such thing as a force of motion. Okay, so the crane is lifting it with the cable. There's tension in the cable. Well, that tension, that cable is what's doing the lifting. Okay, so we gotta be careful about how we define what actually is a force, so that we can identify what the forces acting on an object are. Okay, so with homework 5, you can now go start on a few of these questions here, mainly pertaining to identifying forces and dealing with free body diagrams. And so did you learn to identify the forces acting on an object? So here's some of the forces or the forces we went over in this lesson, and their symbols. And then we learned to represent all the forces with a free body diagram. Right, so this is an example of maybe if we were pulling an IOLAB device maybe there's that screw there that screws into the force sensor. Even if you just pulled on that, there would be some tension, because there's tension in that screw, which is attached to a spring, which is what measures the force that you're pulling with. Okay, and if you're pulling with it maybe on a table, well, gravity is acting downward. Normal force from the table is pushing upward. And as you're pulling it, well, even if you're pulling with the wheel side down, there's not as much friction, but there's still a friction being held back. And so if you are pulling it and it is moving, well, then this would be kinetic friction. And if you were pulling it and you were pulling on it, maybe you put a lot of extra weight on it and you really tried to pull it and it wouldn't move, well, there'd be some static friction keeping it from moving. So we would label this FS. Right, that's it for lesson 14.